Buenas tardes a todos y bienvenidos a la primera sesión de America's HPC Collaboration Workshop. Let me quickly share my slides. If I could get a thumbs up from one of the units. All right, so thank you all for joining us today. Hopefully you can hear me loud and clear. And welcome to the first ever America's HPC Collaboration Workshop. We're a co-located workshop with CARLA 2021, and we're very excited to have you here today. So a little bit of an overview. So the agenda for today will have the introduction, which will be led by me. My name is Veronica Melese Vergara. And then we'll have a keynote presentation by Dr. Elio Huerta and two papers that were selected from all the submissions that we received at the workshop. And we'll also briefly introduce the Women in HPC Latin America chapter that was recently formed, and then open up for a discussion for challenges and opportunities for successful HPC collaborations across the Americas. And we'll like to make sure that you're aware that we encourage participation. So during the talks, there'll be a Q&A session after each talk, but we want to make sure that everybody stays for the open discussion because we want to make this collaboration more active and make sure that everybody's aware of the opportunities and all the different options we have available as part of the collaboration. So bienvenidos a todos, bienvenidos. I'm not gonna butcher Portuguese, but welcome everybody. I put here some resources to give you an idea of what the collaboration is, if you haven't heard of it before. The America's HPC Collaboration Initiative started several years ago with a bird of a feather at SC 2015, if I have my years correct. And there's been continued participation from the group at SC, the Supercomputing Conference in the United States, and then ISC, the Supercomputing Conference in Germany that happens every year. So recently, I want to say it was probably a little bit before, around 2020, we started the American HPC Collaboration website. So the link is over there. And we started doing year-round events. And with the pandemic, everything has been virtual, but we've done several webinars and we're trying to form a community. So if you're interested in joining this community, we focus around HPC and initiatives that could help form collaborations between organizations across countries in North America, South America, Central America, and the Caribbean. So all of the Americas, we're trying to encourage participation from folks from all over so that we can form partnerships and hopefully grow HPC in the region. We have a Slack channel, and this tiny URL takes you to an invite that lets you join the Slack channel. And that way you can stay in touch with us throughout the year. And if you have ideas or if you have anything you want to share about your center, feel free to join. And we will be happy to have you. And to give you a little bit more information about us, and I think we have many of us in the call today. So we have Benjamin Hernandez from Oak Ridge National Lab, Carlos Jaime Barrios Hernandez from Industrial University of Santander in Colombia, Esteban Meneses at the National High Technology Center in Costa Rica, Jose Manuel Monsalve Diaz, the Argon National Laboratory. He actually recently joined our organization group, and Philippe Novo from the Federal University of Rio Grande do Sul, Silvio Risi from Argon National Laboratory, and myself from Oak Ridge National Laboratory. So as you can see, we have several countries represented in our organization committee, and we're trying to do events and we're trying to do different initiatives that will help grow HPC in the region. But we want to hear from you. That's what the whole workshop is about and the BOF is about. But without further ado, I wanted to introduce our keynote speaker for the workshop. Dr. Elio Huerta is at Argon National Laboratory, and he is the lead for the AI. He's the lead for the AI group. And I'm gonna, sorry, I need to jump off. Wait, I wanted to share the screen, but I think I'm gonna pass the ball to Dr. Elio Huerta, and so you can share your screen. I think you can share while I'm sharing. Dr. Huerta, feel free to share when you're ready.
So I hope you can hear me and you can see my slides. Yeah. Okay.
Yes, we can see.
Okay, great. Well, thank you very much for the invitation. I'm really glad to be with you here to talk about high performance computing without boundaries. And I selected a topic that fits in perfectly with this theme. And this has to do with a collaboration that started back in the late 90s at the National Center for Supercomputing Applications with Larry Smarr, who was the founding director of that institution, and Ed Seidel, who had a very ambitious picture or vision for the development of community software for numerical relativity. And the main idea was to try to bring together a community of experts that would develop open source software to solve Einstein's equations. That was the goal. And to create resources, to leverage resources, high performance computing resources, to accomplish this task. And so when Ed Seidel moved to Europe, he created the EU network with the same idea to try to create a community of users that would combine skills from mathematicians, HPC experts, and relativists who were eager to try to solve these complex equations. And over the years, over the decades, this collaboration grew, as you can see in this map, to have now over 300 users across 42 countries in 6 continents. And you can see that this is a collaboration that is active across the Americas. We have several users in Mexico and in South America. And what I want to discuss in these first few slides is how we create the energy, the interest to bring together communities across continents to try to contribute to an initiative. And so what brings together people here is the need to do science, good science, and to have a community that is welcoming, that is diverse, that is inclusive, and that has a common vision. And here the common vision is to understand some problems that are quite topical. They are of great interest to astronomers, to physicists, and all of them share a common understanding of how to work together. And so, for example, here you see a list of different topics that contributors to the Einstein Toolkit have developed over many years. And what you can see here is that there is a commonality in all these topics. There is not a single item that is specific just for people doing numerical relativity. You see that these are topics that everybody that is using HPC platforms worry about. For example, how do you handle parameter files or configuration files? How do we parallelize computation with MPI? When you are solving multiscale or multiphysics problems, either that involve turbulence or you are studying, for example, neutron star collisions, how do we make sure that we have the correct mesh approach to study processes that require subgrid scale precision? How do we handle large data sets with I/O capabilities in these HPC systems? And then once we have this common structure that you see on the left with this cactus picture, what happens here is we develop this common structure, this cactus, and then we have thorns. And these thorns are the specific modules that we use to solve domain-specific problems. For example, space-time evolution, magnetohydrodynamics, etc. And something that we learn throughout this process is that solving the big equations, the complex equations, is just one part of the problem. You see on the right that one of the important aspects of this type of community software development is to really understand at a fundamental level what is happening with these codes. And so scientific visualization plays a key role in understanding how to optimize codes, how to improve it, how to develop better elliptic solvers, you name it. So what you see here that is naturally emerging is that you need mathematicians so that you pose a problem well. You need an HPC expert so that you can write code that is going to optimally use these capabilities. And then you need experts that guide you in the process of optimizing this software. And that eventually you bring it into a mature state where you can automate many processes. And so some of the things that have been possible to study with the Einstein toolkits, as you can see on the right-hand side, obviously binary black hole mergers that in this day and age, they are, very common. They are no longer a big thing that we are eagerly awaiting to discover. They are detected very often by the advanced LIGO detectors. But back in the day, modeling these objects was a big challenge. Now, going beyond vacuum spacetimes, binary black hole mergers, we are now very interested in studying matter systems, and these are neutron star mergers or objects that involve black holes and neutron stars. And this is much more complicated because now we need to couple Einstein equations with microphysics, with neutrino physics, you name it. It is a very complex problem. But then again, the approach here has been, okay, we have a solid foundation, which is how we solve binary black hole mergers. Now we are going to grow organically, gradually, these other modules to simulate this complex physics. And this is how the Einstein Toolkit has had tremendous impact and success with these very ambitious programs. So just to visualize the impact that this work has had on contemporary astrophysics, the original Einstein Toolkit paper has over 100 citations. And you can see that this infrastructure has been leveraged, has been tweaked, has been adapted to study a broad range of astrophysical systems, going from binary black hole mergers, mixed binaries, and this means neutron stars and black holes, supernovae, accretion disks, boson stars, and then even cosmology. So some images that you see here in the top right, for example, you have core collapse supernova. In the bottom right, you have accretion disks. That image at the center is a scientific visualization of the first binary black hole merger detected by advanced LIGO. And then on the bottom left, you have a visualization of two neutron stars colliding. So all these diverse problems can be studied with a common infrastructure. And this is what brings together experts from different domains. And with their combined expertise, their understanding about how to tackle problems with new vistas, new understanding, this is how the Einstein Toolkit has been evolving continually. And right now, there are multiple groups in the US supported by the National Science Foundation that are powering through the development of the next generation of the Einstein Toolkit. I am particularly interested in telling you, if you want a story about how we have been using the Einstein Toolkit and other HPC systems to advance our understanding of gravitational wave astrophysics. So this is going to be the science driver for the rest of this presentation. And here again, as I said before, you cannot disentangle in this day and age doing science with HPC. You cannot decouple this from scientific visualization. So here you see a very nice image of two colliding black holes. And Silvio, who's in the audience, is one of the creators of this beautiful image, where we see two black holes about to collide. And that track that you see in that image corresponds to the gravitational wave stream. So just about 5 years ago, talking about black holes was, for some people, it was an interesting topic. People still doubted about the existence, the reality of binary black holes. Not talking about black holes themselves, but the idea of having two black holes that form binaries and then within the edge of the universe, they get close to each other and eventually collide. That was a dream, right? An idea in the minds of a theoretical astrophysicist. But now we know that they are very abundant in the universe. In the nearby universe, at least, we have evidence of them. And then in 2017, we got the first glimpse of how the collision of two neutron stars look like. And it was an amazing event. And here you see a visualization of this type of system, again, with the Einstein Toolkit. So in view of this, we asked the question, so what is next? Advanced LIGO is observing a ton of black holes when it is in data collection modes, and we are getting very close to the time when it is going to be operating at design sensitivity, and we are going to be observing black holes on a daily basis. So what is the new science that we can do then? It is no longer the excitement about detecting the first pair of black holes colliding or the first pair of neutron stars colliding, but when you look at the census, at the distribution of these objects, the question is, what is the new physics that we can extract from these observations? And just for you to see how much the improvement in sensitivity has taken place over the last few years, in this image, you see in the first two observing runs of the advanced LIGO detectors, there were a handful of events that were reported. But in the third observing run, there is this massive increase in the number of events that are detected. And this is due to the improvement in the sensitivity of these observatories. And here you see again what is the distribution of masses. So here you see that you can start talking about statistics of the population of these systems. Okay, so since we are now at the stage where we can see a ton of these events, how do we go about this? Because you see, this looks like a blessing, right? But maybe it is a curse in disguise. And why is that? Well, let me explain to you. Many of the algorithms that were developed by the gravitational wave community to detect gravitational wave sources are not scalable. They are computationally demanding. And so in the first observing run, when we were observing events like every 3 months, it was okay to use dedicated resources to analyze the data with detail and then understand the properties, astrophysical properties of these objects. But once you start seeing events on a daily basis, then even though you have dedicated computational resources, they are oversubscribed. And so this approach is no longer sustainable. You need to rethink how you're going to do discovery in production scale in a sustainable manner. And so in 2017, I worked with colleagues at NCSA, the National Center for Supercomputing Applications, colleagues from LIGO, those working in San Diego Supercomputing Center that were using the Open Science Grid to help LIGO find gravitational waves. And we put together the supercomputer in the US that was the most powerful at the time for open science research. And we combined that with the LIGO data grid, the Open Science Grid, and a bunch of different technologies to accelerate the detection of gravitational waves. And we applied this for the observation of the first neutron star collision. Sorry, what we found with that exercise is that the most sensitive algorithms that we were using are poorly scalable, not a new discovery. But this was hinting to the fact that if we now have many different gravitational wave sources, how are we going to prioritize how to use these resources? Is there a better way to find gravitational waves? And so this is something that I started doing around the time with my students, and we proposed a new approach. The approach is the following. We still want to use high performance computing, but now we want to develop algorithms that are much more computationally efficient. Algorithms that are going to enhance the science reach of gravitational wave astronomy. And so what we proposed was the following. Let's design algorithms that are lightweight, they are very fast, and they encode information about the astrophysical properties of gravitational waves in a hierarchical manner. And this type of algorithms are known as deep learning models or neural networks. And what we showed is that if we have, for example, a large template of these model signals, and then we train a neural network to learn the properties of these signals, then once you train the neural network, you have all this information about all the different possibilities of binary black holes that LIGO could see. the neural network is just about a few megabytes in size. It processes advanced LIGO data faster than real time. And you only need a GPU, or if you want your smartphone, to process advanced LIGO data faster than real time. And it was a very impactful discovery in terms of algorithmic design and application, and it exhibited great promise. But it is also important to say that at the time, we were considering only the masses of the black holes, not other astrophysical properties like spins. And the algorithms were making mistakes for every 200 seconds of search data. So on the computational efficiency, things were excellent. On the sensitivity, there was room for improvement. But this captured the attention of corporations that are leading the development of AI, and with whom we were working shoulder to shoulder in this particular case, NVIDIA. And so we created this video just so that we get the message out that we are working on novel ideas to accelerate discovery. So this is a nice video. Let's take a look.
I am a visionary, exploring a universe of data to sharpen our view of the most distant galaxies, and studying black holes to help prove Einstein's theory of gravitational waves.
All right. So, when you create this type of approaches, it is great to think about how these ideas can change a field of research. But there is a big gap, if you want. It is a jump into the abyss to go from ideas that look very promising and then transform those into production scale solutions that are adopted by big communities. And so over the last few years, what we have been doing is to take these disruptive ideas into sustained discovery. And how have we been doing that? Well, the name of the game here is to combine artificial intelligence with high performance computing. And with this approach, we now consider a realistic parameter space, which is astrophysical sources with their masses and their spins. And so this 4D parameter space is described by millions and millions of different configurations for gravitational wave sources. Training one of these models with a single GPU may take you about a month. And so this is not good. We need to find other solutions. And so we have been using supercomputers like Summit that is housed at Oak Ridge National Lab. And there, what we do is we distribute the training of these neural networks over many GPUs. And here you can see that we are using over 1,500 GPUs. And what we find is that when we distribute the training with this amount of resources, we can train these networks in about 1 hour. And the beauty is that we maintain the performance of these neural networks when compared to networks that we train with just a handful of GPUs. And this is important because many researchers have found that as you continue to use more and more GPUs, yes, you can reduce the training stage, but the performance of these networks decrease. And so in our studies, we were able to scale the training of these networks up to 6,000 GPUs. But at that stage, there was a degradation in their performance. And so the networks that we are going to discuss in the next few slides are the ones that we trained using about 1,500 GPUs. But at this point, you can see, we see an improvement in the acceleration of these models by about 600x, which is the first time this is reported using neural networks combined with realistic experimental data, not with neural networks that used beautiful images, for example, the image in a data set where you have real objects, but they are beautiful images, very clear, no noise. Here we are including neural networks combined with data sets that are very noisy. The statistical properties of the noise are very complicated because LIGO has data sets that are non-Gaussian and non-stationary. So there is a lot of work that goes into making these algorithms work. And so the idea that we recently presented is that instead of using just one neural network, we use an ensemble of 4. And this is important because what we are doing here is we choose a network and then we train it with different initializations. And so when you feed data from the 2 LIGO detectors, we look at the output of each of these models. And as you can see here, when the models agree that there is a gravitational wave signal and all of them agree, we are not taking averages. When all the models agree that there is something interesting to look at, then the event is flagged, and then we can identify gravitational wave signals. It is worth saying that even though these models are trained with millions over millions of signals, once they are fully trained, they continue to process data faster than real time. And so here you can see 2 of these events. The neural networks process the data, we create the spectrograms. Here you can see this very well-known chirping signature of gravitational waves. And the neural network responds with this very sharp feature that is telling us, I can see something interesting here. And the same for this other binary black hole merger, right? Some of the things that are very good results from this analysis is that when we feed in a month of advanced LIGO data into these algorithms, we identified all 4 binary black hole mergers detected in that data set, and the models made no mistakes. And remember, for the first version of these neural networks that we presented in 2017, the models were making mistakes for every 200 seconds of search data. Here we are talking about 1 month of data, and we made no mistake. Something else that we did for this study is that we are no longer using 1 GPU for inference, but we're actually using 64 GPUs. And we're assigning 16 GPUs to each of the models in the ensemble. So 64 GPUs in total. And using this distributed inference approach, we were able to process the entire month of August 2017 of LIGO data in just 7 minutes. In different words, we reduce time to insight from months to just minutes. And here you see the end-to-end HPC application, using thousands of GPUs to train these models, and then using tens of GPUs to process data. Now, here's where the community aspect kicks in. And how is that? Well, once we develop these models, we want the broader gravitational wave community to use them. So we use a DL Hub that stands for Data and Learning Hub for Science, that is supported by Argon National Lab. We provided all these different models with entire software stack so that people could reproduce our results. And it is important to mention, we are sharing with our colleagues not only the models, but also a solution to reproduce our results. What do I mean by that? Well, we're not only providing models that are containerized, so you forget about library incompatibilities with your HPC platform, but we do something else. And this is the cycle, if you want. We use Summit to train these models as fast as we can and keeping the performance of them at top level. We release the models using DL Hub. And then if you have an HPC platform, either in your university, or you have access to a supercomputer through something similar to the US National Science Foundation or national laboratories, then you can connect the models that we provided in this repository with your compute resource through PhuncX. And what PhuncX is going to do is to call the models and then start the computation on your compute resource, and then tell you whether the results that you're obtaining are similar to those that we reported in our paper, okay? And this approach is no longer a prototype. We have used this approach to reproduce the results that I just told you about. And so with my team, we obtain a set of results, and then scientists at Argon and UChicago reproduce the same analysis, not running the models on this cluster that we call HAL at NCSA, but what they did was to start the models at DL Hub and then distribute the tasks using different nodes in HAL, but external to HAL, right? So what we are doing here is to reproduce the results with a new set of users that have no idea about gravitational wave astrophysics, and they have no idea about how we develop the models, just to make sure this is plug and play. And what our colleagues at Argon and UChicago found is that they can reproduce the same results that we reported. So this is really good, because when you introduce these ideas, artificial intelligence, you want to do distributed computing, you want to use containers, and you put all of this together, people may say, wait, slow down. I want to make sure that I understand what each component is doing, and I want to make sure that I can reproduce your results. And this is exactly what we have done. We have created a platform so that you can go there and in a user-friendly manner, you can go step by step and understand how we're using all these different components. All right, so this is the approach that I just described to you. And I call this a static approach, because what we're doing here is we train the models, and then once they are fully trained, we just put them in this repository in DL Hub, and then you can call the models and use different compute resources to process a given data set. But we can do much better than this, okay? And the approach that we are proposing here, and by the way, if you want to read these results, you can read this paper that we got published recently in Nature Astronomy. What we want to do here is the following. Let me go back a couple of slides. The approach that we now want to follow is one in which we have the models, but we are also fine-tuning the models once we get new data with active learning, reinforcement learning, etc. But now we do the computing no longer, for example, in HPC platforms, but we use cloud resources, because this process of fine-tuning, of improving the performance of these models is not as computationally intensive as when you train the models from the ground up, okay? And I will talk about that in a few minutes. And these are some ideas about how to go forward with the use of AI to find other gravitational wave sources. What I presented so far has focused only on the identification of binary black hole mergers. All right, so this is what I was telling you about. You have now the following issue. You have a big community that is interested in using big supercomputers to develop models, AI models. And people continue to gather bigger and bigger data sets. And so the situation you are in now is that you need to wait long times in queue to train one of these models. And you need to make sure that the hyperparameters that you're using is close to the optimal condition, so that you use your computational resources in a smart way. And once you have a model and it is working well, you're happy, you go and process the data and you find excellent results. But it is a matter of fact that observatories, imaging facilities, etc., their performance changes over time. And so this means that you need to go and update your models. Do you really need to go back to any of these supercomputers and then wait in queue to fine-tune the models? Well, the answer is no. The ideal scenario here is that once you train your models and then you deploy them close to your scientific facility, what you would like to do is to do the computation in situ and then just update the models once you get data sets that are different to the ones that you use for the original training stage. And you can do that through, for example, cloud computing. And what happens here is that you're going to update the models that you have, for example, in DL Hub, but then the computation is local. You don't have to go back to the HPC platform. And so here you can fine-tune the models that you have, enhance their performance, and continue the computation. After some time, when the quality, the statistical properties of the data sets that you are processing are very different to the data sets that you use for the original training, then there is no way to stay in this loop. You need to go back to the HPC platform and then retrain your models. But you can see, you are going to save a lot of time, you're going to save a lot of computational resources if you have this smart cycle here. And this is not just, an idea. This is now being used, this has been adopted in quite a few disciplines. What we need to do is to then share more broadly this type of approaches with other communities. But the cycle that you see here on the top, this is already in existence. And it is being used by many different users. And now we're focusing on these aspects. Okay, it's a very exciting time to do this type of research. So before I go on, let me pause here in case people have questions about what I presented previously. So feel free to just ask your question before I go on.
Thank you very much, Eliu. Sorry, I think I cut off someone, but I see there's a question in the chat.
Exactly. Yeah, that's what I wanted to say.
Okay.
Esteban, I don't know if your mic is working, but the question is, one question is about the latency between task manager and external HAL. The interchange of data is intensive or show a pattern that avoid intercommunication?
Right, that's a really good question. So here we are not broadcasting data. In the paper, in the project that I discussed, the data is already in the HPC platform. And what we do is we just distribute it across the 16 nodes that we have in that supercomputer. And the data processing is super fast. As I said before, when we assign 4 GPUs to a given AI model, the processing is faster than real time. And the IO for that data processing is manageable. If you can process that faster than real time, then you know that there is no issue there. In the case that you, for example, want to broadcast data to the neural nets, for example, using Globus, then that again is not a problem because advanced LIGO data has a latency, for example, if you were broadcasting data to your smartphone, advanced LIGO noise has a weight of about 4 megabytes per second, between 4 to 10 megabytes per second. So it is very lightweight. Other applications like in particle physics are a different ballgame, right? And that deserves another presentation.
Thank you very much. Any other questions for this part of the presentation?
And I would like to say that we welcome questions in Spanish, Portuguese, or other languages. So feel free to ask in your own language if you're not comfortable in English, right? So we want people to communicate. We want people talking to us.
Excuse me, I am from the host, but I have some questions if I can too. How is the data set? How do you get the data set? If you could elaborate a little more on that. I mean, maybe it is a signal and one-dimensional signal, and how it is labeled.
Sure. So the data sets that we use here for the training of the models, to validate them and then to test them, all the noise is provided by the LIGO Collaboration through their Open Science Center. And the data sets are labeled so that you have data in GPS time. So you know when you are looking at the data, what month, what day, what second you are looking at. The data sets are provided in HDF5 format, which is excellent because they are excellent for data compression. And we tend to use those a lot in HPC platforms. When you have a gravitational wave detection in the data sets because LIGO provides that information in tabulated format. So you can always go on and double check that what you're finding makes sense. And it is
So
also important.
excuse me,
Yeah.
the data set is so labeled by humans.
Yeah, it is. Well,
Okay.
the data is collected by the interferometer, and then it is curated by human experts. Yeah, of course.
Okay, so maybe you have a limitation there in the amount. Could be that possible or not?
I think there is no issue with that. I think we have an
Okay.
abundance of LIGO noise,
Okay.
which is great.
Okay, that's great.
Mhm.
Thank you.
Sure. All right, let me move on. So I talked about real-time detection of binary black holes, but as you will know, detecting binary black holes is not the entire story. We have many other gravitational wave sources, like neutron star collisions, or combination of systems like neutron stars and black holes. And while detecting binary black holes in real time is very cool, for the collision of neutron stars, for example, you want to know when that is going to happen ahead of time. And the reason for that is that when two neutron stars collide, they also emit electromagnetic radiation from gamma rays all the way to radio. And they also emit astroparticles like neutrinos. It is hard to see neutrinos for the distances that LIGO is observing neutron stars. If those were to happen in our galaxy, then we could see neutrinos. But nonetheless, we have evidence that when these neutron stars collide, they can emit electromagnetic waves and also gravitational waves. And we want to observe in tandem the emission of gravitational waves with, for example, gamma rays all the way to radio waves. And to do that, well, you need to make sure that these observatories, electromagnetic observatories, are ready to point in that section in the sky where you're going to see a flash of light coming any minute. And so there is a very active area of research that is working on early warning systems, right? This is like forecasting the economy. When are we going to see the next economic crash? Well, here is when are we going to see the next neutron star crash? And we have been working on the development of this type of early warning systems. And so we, again, are combining high performance computing to train the systems. But now we are also incorporating something that is edge computing. People call it edge computing because you want to do the computation in situ, where the instrument is collecting data so that we are not wasting any time for data transfer. And we are not content with just having neural nets that process data super fast. We are even further optimizing the neural nets with quantized neural nets. And so some recent results about this work are summarized in these panels. Here, what you see is the neural net is telling us when it is certain that two neutron stars with these masses, 1.4 solar masses and 1.4 solar masses, will collide. And so he's telling us that the neural net will tell us about 15 seconds ahead of time that an imminent crash in the sky is going to happen. And the neural net also is telling us that around this time, it is very certain that within 10 seconds, something very important in the data is going to emerge. And also, if you look at the location in the sky, it is telling us that it is able to constrain the region in the sky where this event is going to happen to this amount of square degrees. And we conducted these studies for a number of different binary systems that have different eccentricities or ellipticities here. And this is quite interesting. You can see that predicting that neutron stars will collide in tens of seconds is really outstanding. And bearing in mind that here you only need, again, one GPU for this type of predictions. We no longer need thousands of cores to process the data and make this type of predictions. And another point that is worth emphasizing here is that this type of early warning systems work really well for binaries that have low masses, like neutron stars in the order of 1 solar mass. When you start increasing the masses of the binary components, then this early warning system transitions into a real-time neural network that is just telling you right at the spot when a merger is happening. And this is expected, right? Because binary black hole signals stay in advanced LIGO bands for a second or a fraction of a second when you consider the type of masses that we have been observing, like 30 solar masses. But as you consider lighter and lighter systems, around 5 solar masses, 3 solar masses, then these signals stay longer time in advanced LIGO bands. And this is why we can predict with more latency when these systems are going to collide. So this is really exciting. We are now using neural nets, not just for real-time detection, but to forecast when these multi-messenger sources will be observed. And something else that we found here, and this is very interesting, this is something that we found when we developed the first class of neural networks for gravitational wave detection, that when you consider different types of gravitational waves, the neural nets is really not bothered if you use approximated model waveforms that describe these systems, or you use the very last generation of gravitational waves to model these events. And here what you see is that if we use the top-notch waveform model to simulate the collision of these neutron stars, then the forecasting is pretty much oblivious to the quality of this other waveform model that is like almost a toy model. So imagine there were quite a few people developing this sophisticated and adequate model for parameter estimation. And this one was just an approximation that for the detection works equally well. So in different words, the neural networks are giving us an opportunity to go and find these events, even though we may not understand all the physics involved in their modeling. And so this is reassuring. We will not have the most precise predictions for parameter estimation if we don't understand the entire physics of the problem, but at least for detection, this is telling us that neural networks will enable us to find this type of sources. All right, so that ends the other part of the presentation. If you have any questions for that, or I can move on to the final part. Okay. So the final part has to do with multiscale and multiphysics simulations. Then again, this is a central topic for high performance computing. And here I want to play a movie that we produced when we detected the first collision of neutron stars back in 2017. And here we are combining all the elements I mentioned before. General relativity for space-time evolution, microphysics, all the different elements. And producing some of these simulations takes months to complete. And so the question is, now that LIGO is observing more and more of this, is there any way we can try to accelerate the modeling of these complex astrophysical systems? And so with one of my students, I have been working on using AI to study turbulence. And then again, we started with a problem in 2D. And the question was, is it possible for neural networks to learn and describe the physics of turbulence? And this is not, typical turbulence. This is magnetohydrodynamics turbulence. And what you can see in this panel, in these 3 panels, is that there is a lot of complex physics that is happening here, that it is really hard. It is really hard to try to capture with phenomenological models. But what we found is that neural networks are capable of learning these complex physical processes and describe them with much better accuracy than state-of-the-art models. And this got some traction in our community, and we got this award last year at the supercomputing meeting. So what I have described to you in the last 3 sections is that we are at a time when high-performance computing is no longer a single entity, as it was in the past, when we were using HPC platforms for large-scale simulations. Now, HPC is being combined with data. And so people now talk about HPCD, right? Now, systems have benchmarks not only for fault tolerance, for how fast you can finish a simulation using many nodes, but we also have benchmarks for how fast you can train a neural network, something that was unthinkable just a few years ago. How on earth are we going to have Python on a large HPC system? People thought that was impossible. Now we have Python, we have content environments, we have multiple APIs for neural network development. It is a transformation. And so what we are now talking about is we have these simulations that can inform neural networks. We also bring together data sets from experimental facilities, and then we try to bridge the gap between AI models that are trained with simulated data, and then they are fine-tuned to describe reality using data that comes from experimental facilities. And then people start talking about how we can create FAIR, and this means findable, accessible, interoperable, and reusable data sets, so that humans and machines can go and use those data sets in a more useful way, which means that if you want to train a neural network, you don't need to pre-process those data sets. They are ready to go. They are ready to be fed into the neural nets for training, for inference, to enable new discovery. And so when you bring all of this together, HPC platforms, FAIR data sets, you're sharing your models with the community, you have now FAIR AI models, then having this type of approach, the thought, the hope, the expectation is that we will be using advanced cyber infrastructure in a smart way, and we will be pushing the frontiers for new types of data-driven discovery. And we hope to report on this type of approaches in the very near future. And I think I finished this presentation acknowledging my sponsors. And that's it. If you have any questions, please feel free to unmute and go ahead and ask.
Thank you very much, Elio, for the great talk. We do have a couple of questions in the chat. And one is more related to the talk, and the other one is a little bit aside from the talk. So I want to start with Tadeo's question first. So one question to Huerta: is this last example of AI application on turbulent problems employing classical neural networks or physics-informed neural networks or another approach?
This is using classical neural nets. Yep, but you're right. The next step here is to incorporate physics knowledge into how we train these nets, into how we construct the architecture. Yeah, and that's the next step. You're right.
Great, thank you. Are there any other questions specific to the material in the talk? If not, I can go ahead and ask Philippe's question. Oh, Philippe, if you want to unmute and ask your question. Thank you. I see you here.
Go ahead. No, just Huerta, can you say to us a little about your trajectory until be in the US in the Argon lab? Because it is a panel of America collaboration, so we would like to know how you go to America, to a lab in America.
Right. So my trajectory starts in Mexico City. I got a bachelor's degree in physics at the National Autonomous University of Mexico, or UNAM. And my mentor there, Sergio Mendoza, he was a PhD student in Cambridge in the UK. And so, you know, sometimes your mentors play a big role in your decisions. And he encouraged me to go to Cambridge, and so I did. I was fortunate to go there. I completed a master's in math in Cambridge and then a PhD in theoretical astrophysics. And then after that, I moved to the US, where I joined a team at Syracuse University that was very active, that is very active in gravitational wave astrophysics. And there is where I learned about, you know, all these scientists that were very actively working to develop algorithms to find gravitational waves. This is where I learned about their capabilities, their limitations. And then Ed Seidel and Gabriel Allen invited me to join the National Center for Supercomputing Applications. I started working more on HPC applications for gravitational wave astrophysics using the Blue Water supercomputer at the time, creating a team that was the NCSA Gravity Group. And
so
then
you go to Urbana-Champaign?
That's right, yeah.
Yeah, nice.
Mm-hmm. And well, you know, it is about being adaptable and then being open to new ideas. I created the Center for AI Innovation at Urbana-Champaign, where I work with scientists in many disciplines to understand how to apply AI for their grand challenges. And then this year in April, I joined Argon National Lab and U Chicago to play a role in their AI for Science program.
Very nice. Thank you.
Yep.
Yes, very nice. That's interesting to know how your trajectory also. Any other questions for Elio?
I do have another question, and more or less related to that, because as I want Elliot to give some advice to our audience here. So I just highlighted some of the things that you mentioned in the first part of your presentation. And by the way, thanks for accepting to present it today, and that was a great talk. So for example, you mentioned efficient algorithms, right? And as part of that, deep learning being one of the most efficient algorithms for the science problem that you wanted to work with. You also mentioned the DL Hub, right? And that provides some models already computed for users, for final users, and that is great. And another idea that I really like is that one of updating models only when needed, right? And so you don't need to rerun on the big islands. And I think all that is applicable, right, to our audience coming from the Latin American countries, right, where most likely you don't have access to the big supercomputers, right? So I'd like to know your opinion on that, and if you have any advice for them on how to be efficient with the things that you have, right, at hand. And yeah, I'd like to know more about that, or your vision about that.
That's a great question, Silvio, because even if you're in the US and you have access to these big systems, I mean, the reality is that to get access to a supercomputer like Theta or Summit, you need to have the skills and to demonstrate that you are ready to use those systems, right, at a scale. That's not easy to accomplish. You need to work towards that goal. And admittedly, people really don't need to do that. If they are really interested in just using the models, well, they should get access to the models. And I think the DL Hub is a great step in that direction. If people want to learn how to use deep learning models and they have a data set that is ready to use to do inference, for example, then they should be able to just go get the model, then run it on the data, right? And this is, for example, what big corporations like Google, like Facebook and others have done. They create these massive models like GoogleNet, BERT, etc., that it would be really hard to train even with the systems that we have in DOE or NSF. But people are able to use them, and then they can do marvelous things with those models. And this is the type of approach that we want to mirror here. People have different needs, different capabilities, different skills, but we all want to use models. And so we are trying to bridge that gap. You want the model, here it is, go and use it. You find something that is not working well, let me know, and then we can work together.
Great, thanks for your answer.
Mm-hmm.
Thank you so much. Unless there are other questions, thank you again, Elliot, for your great talk today. And I hopefully you stay for the rest of the event so we can have a discussion during the open discussion. But thank you again. And I think we can proceed with our next part of the workshop. So we have 2 papers that were accepted to the workshop, and I will invite the presenters to share their screens. We already tested this. So first up, we have Dario De Matis.
Yes, thank you. I will share my presentation. Just wait a minute. I am sharing right now. Okay.
All right, I can see your slides.
Okay, just wait a minute because something is not working very well here. There, then, a second. Little more. Okay, I think I am ready.
Sounds good. Well, I'll take it away, Dario. Floor is yours.
Thank you, Veronica. Okay, good afternoon. First of all, I want to thank CARLA committee for inviting me to participate in this workshop. To present my postdoctoral research. It is a great honor for me. And to introduce myself, my name is Dario De Matis, and currently I am a postdoctoral researcher at the National Scientific and Technical Research Council here in Argentina. For now on, called them CONICET. Today I will talk about my postdoctoral research, whose title is Towards an Active Foveated Approach to Computer Vision. So this work is a collaborative effort between researchers at CONICET from Argentina, from Argon National Laboratory and Loyola University Chicago from the US. Our collaboration began when I was still a graduate student at the University of Buenos Aires under the direction of Dr. Silvano Sanuto, that is here on the right, and Dr. Alejandro Wenzelboim, too, as a co-director. It was about in 2015 when our group contacted Dr. Silvio Risi to discuss the possibility of running some bio-inspired computational models on Argon National Laboratory supercomputers. And given the vast experience as both an educator and as a computer scientist and software engineer, Dr. Kate Chairovatukal was invited also to join the team shortly after the initial conversations. Well, what follows was the establishment of a distributed thesis committee with advisors in Argentina and co-advisors in the US. Also a remote access to Argon leadership computer facility resources through director discretionary allocations, which grant resources to use in the facility. Of course, a lot of MPI and OpenMP learning, including my participation in the Argon training program on extreme scale computing in 2018. That was in person. There was no pandemic there. And the publication in some journals like PLOS One and Frontiers. My PhD graduation was also an event in the middle of the pandemic. A pandemic was to happen in order to be graduated, I think. But now I have a postdoctoral position at the CONICET, whose main progress I am presenting today. Those are some of the papers as a result of this collaboration. Phonetic acquisition in cortical dynamics, a computational approach in PLOS 1. A computational theory for the emergence of grammatical categories in cortical dynamics in frontiers, and a conference paper that George presented in Prague in 2019 towards high-end scalability on biologically inspired computational models too. So in order to get into the project in itself, let's talk about the major challenges faced by today computer vision. In the classical supervised computer vision deep learning, we have, as everyone must know now, an input image, a convolutional layer, a fully connected layer, and finally the output prediction. And errors in the prediction are backpropagated continuously during learning, adjusting the synaptic weights until the network achieves some performance threshold for some task. The most well-known task is image classification. For instance, to classify the image that we see in the figure as an instance of a car. But supervised computer vision requires very large data sets, all labeled by humans, which is very, very expensive. And you always have to think that humans label those multiplied by millions. So it is extremely expensive. And for the volumes of data managed today, it is, I will say it is not viable anymore that a human has to label data. On the other hand, computer vision models are extremely expensive from a computational perspective, are huge. For instance, in real-world applications, digital cameras firstly provide the visual input, no? And then hardware runs the needed AI to make inference, for instance. But images has to be transferred through the network infrastructure with process-evident drawbacks, producing enormous latency limitations of centralized computing. Well, in some computer vision cases that could depend on near real-time video processing, demanding AI solution of the edge computing devices. No, the previous speaker talked about edge computing, but for those that doesn't know what is edge computing, simply said, it is a distributed computing paradigm that brings computations and data storage closer to the sources of data. In this case, in this example, it goes closer to the cameras. With this, information is processed, input information that are the images, high resolution images, are processed directly in the cameras. And what is transmitted is the bounding boxes and the classification information that is much way less information than transmitting all the images as in centralized computing. But the question is how to fit computer vision models in modest edge devices, because edge devices are embedded in the cameras, so they are very tiny. How to fit a computer vision model that is used to be run in a supercomputer, but fit it in a digital camera? It is difficult because computer vision models are truly big. I don't want to extend too much this presentation, but my proposal is that plausible solution could come from a combination of two strategies. One is self-supervised learning, which is used to alleviate in some way the huge label datasets demands. And the other is to inspire our models' designs on biological aspects of visions, such as foveation, for instance, in order to reduce computational demands of computer vision models. one of the most used techniques in self-supervised computer vision is using unlabeled data by means of contrastive learning. The approach is the following. You have an image, you augment the image, produce two different augmentations, and you teach a neural network, in this case, a convolutional neural network, to produce output that are as similar as possible when the augmentations come from the same image, and as different as possible when the augmentations comes from different sources, images. So in this way, the network acquires a lot of features from the statistical distribution of the data set without labels. Okay, there are, those are the typical augmentations that are applied to those strategic algorithms: crop and resize, flipping, color distortion, cutouts, rotations, blur and noise and filtering, among others. But I think human visual system has a lot in common with this mechanism. In fact, what I think is that we indeed do such augmentations every day throughout our life. In fact, the real fact is that we do until 5 fixation of our eyes per second. That means that even when we see a static and well-defined image, when we fixate, our retina is receiving 5 very different versions of such an image per second. Such a different version consists of different fixations at different locations of the image. Even so, we see a static and well-defined image. Evidently, or maybe it is so, our proprioceptive system is telling us that we are seeing the same image independently, that our retina is receiving 5 very different versions of such an image, because we are not moving. We are fixating at different locations without moving our neck or our head. But now, if we deviate our gaze to another image in the room, for example, our proprioceptive system will inform us about that. And we will be aware of that, and we will be able to discriminate the new image from the last one. This is something like the self-supervised, the contrastive learning that we see previously. And this is the main point in this research. And so it is necessary to talk about the foveation a little bit to understand this presentation. As we can see, this is the eye. This is the retina. Those are angles whose origin is the fovea. The fovea is the center of fixation, where the center of our gaze. And this is a reproduction of in a chart of the distribution of cone and rods that are photoreceptors in the retina. We will concentrate in cones, since roads are for night vision and we are interested only in color vision, that is during the day. The dashed line is the distribution of cones in the retina. And we can see there is a very, very high resolution at the fovea, and that resolution decreases sharply in the periphery of the fovea. This distribution has, as a result, the following slide, that is this one. The resulting phenomenon is that we see images like the one on the left as the one on the right. If we are fixating at the V, of course, that is, we see a very well-defined image at a tiny fraction in the center of fixation, that is the fovea, and all the rest is very diffuse, very low resolution. Let's do an exercise together. If you extend your arm and put your thumb up, approximately your thumbnail is what you see at high resolution. All the rest is virtually very poor resolution, but we do not even realize about that. This is because our visual system is working very hard to make it happen. Furthermore, the foveated vision is the reason why we need to saccade and fixate at certain location in the image in order to define it, to could classify it, or to could detect the objects on it. Okay, so our strategic endeavor in this project gains inspiration from a developmental perspective found in certain changes in the behavior of the fixation that throughout ontogeny. The behavior of fixations from the moment that we are childs to the moment that we are adults vary a lot, from reflexive fixation to volitional fixation, more well-intentioned and intentional, to say it in some way. So that is the inspiration. The first step in our development was to create a foveator. We used NVIDIA Daily Library to do that. To simulate the foveation process found in some biological agents, such as some mammals, we generated 5 spans, as we can see on the left here, from the same image around a fixation point that is here, the fixation point. All the spans has the same number of pixels, 30 by 30, no? But some of them sample the complete original image. As we can see, the number 1 has the complete original image, but the number 5 has a very tiny fraction of the image. The smaller the span, the larger the resolution, and vice versa. And this is what we use as a foveator, as a simulation of the foveation to feed a network. The second step is to pre-train a ResNet architecture by means of self-supervised learning. We use a contrastive learning as seen in the previous slide. This is on the left here. But the distinction in this is that the novelty here is that we do not only use augmentation normally used in contrastive learning, but we also use our foveator. We use a foveated image as an augmentation, additional augmentation factor in this architecture. That is, we train a backbone, that is the ResNet, to distinguish foveations that come from the same image from foveations that come from different images. And in that way, we train a backbone in a self-supervised way without labels too. And it is pretty natural to add foveation as an augmentation strategy. It could be that humans use the same. And this is the third step. In this step, we developed an architecture based on a transformer. No? Basically, our pre-trained backbone process a sequence of fixation from our foveator. As we can see here, this is the backbone, this is the foveator. And this is a sequence of fixations. Then the transformer encoder processes such a sequence of representation delivered by our pre-trained backbone. And finally, the transformer decoder returns a series of predictions about the image class by means of feed-forward networks. The prediction of the output is an average of the softmax vectors returned by the feed-forward networks at the end of the decoder of the transformer. The idea of this network is to provide an amalgamation of the sequence of foveated fixations. Is to give an identity or give an entity character to that sequence of fixation that could help to process a classification in some image of the data set. We use the ImageNet, so to say, in order to train those networks, all those networks. Finally, to make it more complicated, we added a reinforcement learning mechanism to guide the saccadic behavior, following the developmental approach that I stated in the previous slide. The aim is the following. The transformer architecture shown in the previous slide is here, and is taken as the environment by the reinforcement learning mechanism. As we can see, the states are the outputs from the foveator. This is the state in the reinforcement learning jargon. The rewards from the transformer, the rewards that goes to the reinforcement learning are the performance from the transformer. And the actions from the reinforcement learning are the coordinates of the prospective fixation, the net fixation. It produces, the reinforcement learning will respond with the best option of the net fixation in order to do a good classification performance. So the main idea in the reinforcement learning algorithm is to learn the dynamic of the environment. That is, to learn the dynamic of the transformer in order to choose the best actions to get better classification performance, in order to choose the best locations of fixation to make the transformer classified better the images. There is a challenging situation here, no? Because there is an interaction between two networks. Is that the environment is the transformer, and it is highly dynamic when it is learning. So it is difficult to follow by the reinforcement learning mechanism. Maybe some strategies could be to frozen the transformer and make the reinforcement learning to learn, or vice versa. It could be analyzed later. Finally, this model was implemented in high performance computing resources using a parallelism scheme generally utilized in PyTorch. The idea behind this scheme is to produce a model replica, as we can see here. It is produce a model replica for each rank and split the dataset in different shards. One shard is processed by each model replica independently. As we can see, this image is divided in 3 sections, A, B, and C. So let's analyze the image in its section. Each little square in A represents a batch of images. As can be seen by the color from one epoch to the following are varying. So the set of batches belonging to, the color varies from one epoch to the other. That is in order to make that that the pipeline, each model replica process all the data set and not always the same shard from the data set. So you make so to say the combination of shards in each epoch, and that improves training a lot, and that is done by the NVIDIA Daily library. In B, we show the foveator, no? The foveator implemented with NVIDIA Daily. It consists in 2 pipes. Pipe 1 loads and decodes a complete batch of images, while Pipe 2 produces a set of fixations from such a batch, as we can see here. F fixations for each batch, for each image in each batch. In C, we show in sort to say the training procedure of each model replica. The process is the following. Is interesting. First, each model replica produces a forward pass of its respective batch and compute its loss, its own loss, and its own gradient. Secondly, the gradients are communicated among all ranks, averaged in each rank. As we can see, the arrows here try to illustrate the communication of the gradients. And then each model has all the gradients at hand and can average them. And finally, each model replica will have to adjust the weights based on the average gradient. That is the parallel. This is the main idea in the parallelization scheme of this approach. Well, what more we have here? This is this is a chart showing strong scaling efficiency plots as a function of the mini batch size, as we can see here on the horizontal axis, and with different series for different number of nodes, as we can see here from the colors. There is a kind of tendency there. Those are very preliminary experiments of the parallelization, but efficiency tends to increase with the mini batch size. Efficiency tends to be a little better when the mini batch size increase, and the efficiency decrease with the number of nodes when the number of nodes increases. That is obvious because you have much more communication. We reach a maximum of 16 nodes with in theta GPUs, it is 8 GPUs for each node. You have 128 GPUs. Okay, so let's discuss a bit and close the presentation here. The main conclusion here is that this work is currently under progress. It is a in progress work, so to say. So we are preparing experiment for classification at first. Maybe later we will incorporate detection. The good news for this is that all the implementation is already done, and now I have to make some modification to the architecture or to the experiment and see what happened. Everything is implemented, everything is working apparently well, and you have to start to play now with the hyperparameters that you have to modify the architecture a little bit. But one of the problems that I am seeing right now in this implementation is that the transformer positional encoder, it is in the transformer positional encoder. I mean, I encode one position per fixation. It is not normally done in that way in vision transformers. It throws away all the position information inside each fixation. So this brings me great computational savings, but on the one hand, but we lost a lot of information on the other. Maybe I have to modify a little bit that. And another important aspect is in the reinforcement learning mechanism and how to get it follows the evolution of the environment that is the transformer. You have, so to say, something similar to the GANs network, generated adversarial networks, that you have two networks that have to learn back and forth with one another, and you have a similar scenario here, and you have instabilities there. So it could be difficult too, but there are a lot of papers that brings reinforcement learning mechanisms that are very well suited to learn in fastly evolving environments. So those are the problems, those are the architecture implemented, and the future development. So thank you very much for your time. It has been a great honor for me presenting here, and highly appreciate the chance that you have given me.
Thank you very much, Dario. Great talk. And let me open the floor for questions to see if anybody has a question for you. If not, I have one that I wanted to ask.
Okay.
Let's see, Silvio, turn camera on. And Carlos, do you have a question, either Silvio or Carlos? If not, I'll go ahead with mine.
So, Dario, I would like to know if you have any advice for the attendees, for our audience, based on your experience, right? So you were working from Argentina, got some resources in Argon National Lab, and that's part of what we're trying to promote here, right? People accessing resources in the US, we're trying to facilitate that. So tell us about your experience there.
Yes, thank you, Silvio, for the question. If I had to say something, I have to say that I have to demystify this, you know. I already started without knowing almost nothing about parallelization and high performance, and I started learning when I start to apply for resources. And remember, the first time I apply for resources, I get it rejected with suggestions, and I started to learn new things. And it is a word, it is very easy to get resources in the US. For me, it was very easy. It was very difficult in my country because the resources are not abundant here. And in the US, it was very easy because they are very open to new projects. They don't ask you many questions about if you have already run experiments previously, because if you don't have experience and your project in your project you have not run too many experiments, you have nothing to show. But they don't ask those kind of aspects. Maybe with a pair of experiment and results and scaling efficiency plots, you can start to ask for resources, and they are very open. In fact, my work, when I started to ask for resources, my work was in a very primitive stage, and they accepted me, and they are very open. So if I have to give an advice in that respect, you don't have to be afraid of, because you say, oh, Argon, my gosh, they will reject me. No, this is not in that way. They are very open, very good people. They are for help you. The pandemic has bring, I have not to say that, but the pandemic has bring great advantages in the fact that sometimes one don't have the money to travel to the workshops. So the workshops now are very open and virtual. So in Argon, you can learn a lot about throughout the workshops. And you have assistants with professionals. You can connect with them by Slack. And in fact, I am the PI for a director discretionary allocation on Theta GPU, thanks to a workshop that I made, because they helped me to implement my model, and I could apply for that, and anyone can do that, anyone. So that is my advice. Go ahead and apply.
Thank you.
You're welcome.
Yes, thank you very much. That's very much
You're
something we want to promote and let people know that the resources exist and they're available outside US. And it may take a little bit, like you mentioned, like the first time it was rejected, but then with the feedback, and we're more than willing to like just meet with you if you have questions and try to figure out how to get the application so that it has all the components it needs to be. And that's sort of the whole point of the Americas HPC collaboration. So it's a great to hear your story, Dario.
Yeah, thank you. Thank you very much. Without exaggerating too much, they saved me my PhD, you know, with the resources. So I pretty grateful about that. And thank you for inviting me.
Awesome. Any other questions for Dario? If not, I can, in the meantime, invite Luis Campos Duarte, so you can share your screen. Is our next speaker for the paper session.
Yeah, hello, can you hear me?
Yes, I can hear you.
Okay, perfect. Well, hello everyone. Congratulations, Dario, for your work. It's an awesome presentation, and well, congratulations. Well, my name is Luis Javier Campos, and today I'm going to present the audience of CARLA 21 our work titled An Evaluation of Ray Tracing Based Model for Photorealistic Image Rendering of Confined Plasma in Accelerators. Of course, I'm the presenter, but this work also have the name of Diego Jimenez, Silvio Rizzi, and Esteban Meneses.
Can you share your slides to make sure that we can see?
Oh, sorry. I thought I was presenting, but The only thing that I was assuring it was I'm hearing nice. I guess so. Can you see it?
Oh, yes, there it
Okay,
is.
perfect. Let me okay. So as I mentioned it, hello. My name is Luis Javier Campos, and today I'm going to present our work titled An Evaluation of Ray Tracing Based Model for Photorealistic Image Rendering of Confined Plasma in Accelerators. If some if there's some inconvenience with the call, I can see anything of Zoom, so don't worry if you can if you need to reach me out. Well, today I'm going to present the agenda. First, we have the introduction. Then I will show the problem description. Then the solution we are proposing and the evaluation method that we create for this solution. So to start, plasma discharges have been carried in Costa Rica thanks to construction of the SCR1. In words of the Dr. Ivan Vargas, 1 gram of this plasma confined is the device. In this device, sorry, it can supply electric power for 8 homes approx. 8 homes approx for a month. Here we have the SCR1, as you can see. So the development of plasma confinement devices can be very expensive and dangerous. Plasma physics also can take advantage of HPC techniques and parallel programming. As an example, we developed a BS Ultra code that calculates and simulates the particle trajectory in minutes. It may be a large number of particles actually, and also the largest particle number that have been simulated as a software benchmark have been sorry 1,000,000 particles. And also with using the result of the simulations and using ParaView software, scientific visualization images and particle animations has been rendered as, and they have an important role in communication and research. The idea with this work is to create a workflow of plasma physics, for plasma physics researchers that allow them to get a set of photorealistic images of plasma confinement using computer graphics techniques such as ray tracing. So in order to evaluate these images or the images generated by our model, we had to define a concept called visual plausibility, which it means the quality of seeming visually or reasonably or a probable depiction of reality. So here we have an example to just to clear the concept. Here we have a different representation of the same person, Barack Obama, the 49th president, or 44th, I guess, president of the United States, in order to illustrate the concept that we have mentioned. In the center, we have a real picture of Barack Obama to use it as a reference for visual plausibility evaluation. On the left, we have a representation that, although is non-realistic and it's not like a real appearance representation, we sure know who is, and that's why this is a low visual plausibility representation. On the other side, the right side, we have a very realistic draw, which is a high visual plausibility representation. As you can see, we can evaluate the visual plausibility of any representation using any scale that we want, maybe 1 to 10 or 1 to 5. So the problem description. So here you can see how it looks like in real life, like plasma discharge. So there is a problem with this because as we can see, plasma discharge in accelerator, we're actually not able to see plasma volume shape, right? Developing accelerators and taking pictures from inside in order to see plasma is very, very expensive. If the accelerator design does not take into account the locations to place the camera from the beginning, it's very difficult to put that put that places after it has been constructed. You cannot take pictures of plasma confinement until the chamber is completely built and working. Testing new accelerators course configuration would complicate even more the process of taking pictures. Um, uh, so we can summarize our problem in two questions. The problem is, the first question is it possible to generate a framework that allows us to generate a photorealistic images of different accelerators configurations at low cost? Or even better, can we generate those photorealistic images of devices that have not even been built yet? So here we have an example of real discharges of plasma. This is a real picture. So this is the goal for us, for our model to generate. So this is the part of the solution that we're proposing. The design pipeline, here we show a pipeline that describes the process that we designed for converting the output data of the simulation that we mentioned into an object that describes correctly the plasma volume shape. First, we have TXT files that shows each step that a particle made in the simulation. Then if we track all the steps and get all of them together, we can reconstruct the plasma surface of it. So in that case, we select the biggest simulation file because the more data we have, the more accurate surface we will get. And once we have the biggest file selected, we convert it into a X, Y, and Z file. Then compute the normal for each of one of those points of particles position. And finally, we used as input for the screen Poisson surface reconstruction algorithm. It's a very well-known algorithm to achieve the surface reconstruction. So graphically, we have this result of the simulations, and we want to convert it into a solid surface. So in other words, we have to convert this representation into the left representation into the right representation. The second part of our work is to place that object into the scene and give it some plasma-like appearance. For that matter, we use the well-known Phong reflection model that Paraview have built in to describe how the light behaves when touch the object. In our specific case, we only need the diffuse lighting since it is the attribute that most affect our model. In other words, is the attribute that brings more light to our object without affect its transparency. Added to latter, we also modified the object density, finding the sweet spot between light emission effect and the transparency or low density aspect that the plasma have. Here we have some tests that we made in order to achieve the correct appearance. And in addition to that, we explored with another attribute that seems quite useful sometimes, but not in this case, the luminosity attribute that makes our object into a black body object, which means that we remove all the transparency of it. This looks interesting, but when we don't want to render a realistic representation, but we want to catch the audience attention. It means that if we want to make a non-realistic representation, but definitely the eye catcher representation, definitely we want to go to this attribute luminosity in order to make it more I don't know how to call it, but interesting to the first sight, to a first sight. So the results that we got using the model that we described we just described. Here we have different rendered images that are resulting from our model. Also, we have a material according to the accelerator real material. It was aluminum representation, so it made the representation more realistic. And also we want to make an image that only represents the plasma, taking out the accelerator chamber, because although we add realistic attributes to the chamber, the model was only for the plasma, so uh, it's more accurate to evaluate the plasma in by itself in the presentation that if we show with the accelerator. So this is the part that it's new. Actually, we haven't showed the evaluation part to the community, to the scientific community. And well, the evaluation method consisted into 18 people related with the Plasma Physics Laboratory of Costa Rica Institute of Technology. They evaluated their work, and they were willing to do it. So researchers, assistants, and students answered the survey and made the evaluation. The evaluation reveals details like how experienced with plasma the people are, and their opinion of how the plasma should look like. That it's we ask a couple of questions in order to uh, uh, context or made a context of the evaluators in order to know how much they know about the plasma and how it should looks like um, in a representation. So here is the first question. The first question is, which is your relation with plasma physics? Here we have the 15% of the people that answered the survey. They were researcher. It means like nine persons of the inquiries, they were researchers. The 16.7% there were students, and the 33.3% they were research assistant, which it means they all have worked with plasma or at least in a related field. And a second and third question, well, the second was, have you worked directly or indirectly with high temperature plasma discharges? As you can see, mostly all of them, they had worked with discharges. And also, most of them, the 88.9% of them, they said they have seen a real photograph of plasma in confinement devices like accelerator or tokamaks. So as we already know, they have seen plasma discharges, they have seen plasma in real life, so they are good evaluators for images. And here we have the fourth question that we asked, sorry, according to your experience working with plasma, how does the plasma should look like? And the answers shows a lot of coincidence between them, but and between them and their work. But in general, the words like gas, sparkly, glowing, region, shape, fuchsia, light, gradient, gaseous, flow, glow, light, luminous, intensity, they were a common keywords that we found in all the answers. And the fifth questions before the evaluation, it was the, did you know the concept of plausibility before taking this evaluation? This was only for our interest, because we wanted to know if they already know a concept of only plausibility and to be sure that they read the concept that we created in order to evaluate the images, because this is an important concept that they have to be clear with that. So the 50% said that no, and the other 50% said yes or maybe. But with this question, we assured that they read again the concept that we created. So we sure about that. So this is the first image evaluation. This is not an image from our model. This is another of the first try we had using a ray tracing model that it's called PBRT. This is a try or an experiment that we had. It not achieved the result that we wanted, or that we desired, but it's a kind of representation. I don't know. So we asked the evaluators to rate each image from 1 to 10, considering the visual plausibility image score. So here we have a mean of 5.65 and standard deviation of 184. Here we have the another thing that we also consider important is that if the image have like a mean up to 7, it's a good evaluation, and down to 7 or 6 or less, it's like a bad evaluation for model. So here we have a bad representation but good evaluation in order to I don't know, test if they know well the visual plausibility concept and apply it to the image evaluation. And here we have the second image. This is an image rendered with ParaView, and we used 1 million particles. It does not pretend to be realistic. It is just a representation of 1 million particle simulation, and the objective of this image is only compare another type of representations in order to compare where we get to the realistic ones. So this image had the lowest rate. It has the mean of 3.8 with a standard deviation of 1.99. Nothing more much to add in this in this image. And we will get to the third image evaluation. This image, as I mentioned, is using the attribute that I mentioned before. It's called luminosity. This is a non-realistic representation, but definitely it has a good it had a good evaluation score. Although it's not realistic, we can see that with a mean of 5.55 and a standard deviation 1.88, it has a good it has a good evaluation, because the people in the answer tell that although it's not realistic representation, it could make a good it could make a good representation in sometimes that they wanted to impress the audience, as I mentioned, or want the attention of, I don't know, like of founding resources or something like that. It's a cool almost realistic because a representation because of the accelerator appearance. And this is definitely our model that we built. Hello, can you hear me?
Yes.
Yes.
Okay, perfect. So this is the fourth image evaluation. This is definitely the model that we built, and as you can see, the results are very good. The standard deviation of 0.94 with a mean of 8. As you can see, it's a very realistic representation. It looks like the images that we saw before, and and the fifth image using it without the accelerator device also had a good result, almost 8, with a mean the 7.94 and standard deviation of 0.99. It has a good score, and almost all of them vote that it is a very high visual plausibility representation. So another analysis that we had is that according to the relation of the role and score of the people that evaluate their images, as we can see, the highest the role in the laboratory, the highest evaluation or better evaluation that we have with a better standard deviation. Maybe it's something that it's related or not, but it's definitely a very interesting relation that we get. So getting to conclusions, the current work introduces a computer graphic model that builds a visual plausible representation of confined plasma using the data generated from a mathematical framework. The results confirmed that the images generated by our model obtained a high plausibility score according to the expert criteria, which we support the proposed thesis that we had in this work. Also, we want to mention that another evaluation that we want to add to the paperwork is the p-values analysis for the evaluation results in order to concretize or make more stronger our work, and that's it. And that's it. This is the thing that I have prepared for today. Do you have any questions? Here you have my email in case you want to reach me out, and thank you very much.
Thank you very much, Luis. Any questions from the audience?
I really want before if anyone have a question, I really want to be thankful or thanks to Silvio Rizzi for all the help that he lent me. The facilities that Senat and the Argon National Laboratory made us, because we run some experiments in Theta, and we had some collaborations with them. So we're very grateful to work with you guys, and of course we're very happy in order to grow this Latin America collaborations in HPC.
Thank you so much. And I guess one question I had that is similar to Sylvia's question earlier, like how you enable this collaboration with Argon and Senad, like how are there any advice or any lessons learned that you were like, maybe don't do this, but yes, do that to have a successful collaboration?
Yeah, well, definitely I should say everyone should talk with their peers in order to asking them for help if they need it. I mean, there's a lot of people that doesn't say anything because they already think that it's impossible to collaborate with someone like, I don't know, like Argon. It's a big laboratory in the United States or something like that. But definitely, it's not an impossible thing. Definitely, you should reach out as far as you know someone or you have a contact with anybody. You have to reach out in order to ask for help and to see if they are able to help you. I get it's very straightforward once you ask, but I guess the barrier is just to connect with people, and I guess that's it. That's my advice: connect with people and I don't know, make your best effort in order to the community grow up.
Thank you so much. Any other questions from the audience or from the folks on the panel? All right, everything is a bit quiet today, but I wanted to say thank you to both of our presenters and to our keynote speaker. This is it's great to be able to have the first workshop, and I think the material presented today shows that there's already many successful collaborations going on, and we want to amplify those voices. We're gonna take a quick break. So since we have already been going on for a little bit, so we're gonna have maybe like a 5 to 10 minute break. So let's be back at 4:10 Eastern, which I guess will be 3:10 Mexico City time. So we'll have a break and then we'll continue with the other part of the workshop, which would include open discussion. So please come back, but we'll have a coffee break until 10 minutes from now. Thank you again to everybody.
Okay.
All right, I think people are coming back. Glad to see again. So next in our agenda, we just had a small blog saved, reserved to kind of talk a little bit about, let you know about the Women in HPC chapter. And let me see if I can share my screen. So if you're not familiar, the Women in HPC organization was started a while back, but it's an international organization that promotes diversity and equity in HPC, and it supports women, but it's available, I mean, it's open and accepts members from everywhere. And this past year, thank you to CARLA Oshoff, who is in the currently in the call, if I remember correctly, she was online. And also Paula Bergelet, and a few other people from the different workshops. From the previous CARLAs, we had a Women HPC workshop in Costa Rica and in Ecuador, and I think even before the Costa Rica started. And Carlos, you're one of the founding members of the Women in HPC workshop. So if you want to say something, you're welcome to. If you were still on and not on mute. But in the meantime, I just wanted to let you know that thanks to all that work, we actually filed for an official chapter. So as of like this year, we are listed as one of the official chapters in Women in HPC. So we have the Latin America Women in HPC chapter, and anybody online, you're welcome to join the chapter and join the Women in HPC organization. And if you're interested in participating in our events, and our chapter is a regional chapter, so we're not a specific organization, but we're trying to have a Latin America chapter of Women in HPC, and we're officially part of the Women in HPC organization. And you can read more about it in the website. I can put the link in the Zoom. And Carla and Paula, if you are online and want to say a couple of words, that would be great. But if not, that is okay too. I don't want to put you in the spot. Let me paste in the meantime the chat. So sharing. And I see both Paula and Carla. I see you right there. Maybe you want to say hello. Carla, you're muted, but you can unmute. I think you're trying to say something.
Okay, so now I think I can talk. Yes, yes. I would like to share, maybe just to talk a little bit, but I think I cannot share. No problem. Okay, so yes, I cannot share. No problem. So I would like to mention that the chapter is part of the initiative that started in 2018 with the invitation of Carlos Barrios. He was the coordinator from the edition. Hello, Carlos. He invited me for the initiative to start the workshop. Similar to the same initiative that have been going on supercomputers conferences. So we started on Colombia, and then since then, this year we had the 4th edition, and was very nice, very successful. And it's very interesting that each one of the editions that we have a coordinator, a local coordinator that help us to bring the local community. So this is very interesting. So in such a way that the workshop is improving and the community is growing up. And then now we are part of this kind of international woman initiative, Women in HPC, that the intention is to improve even more and to give even more information about such a kind of initiatives for women that are working on STEAM areas. So I think that's all. Thank you, Veronica, for this opportunity to talk about this chapter. And thank you, Carlos, for the initiative.
Thank you, Carla. And I also was going to say, maybe you want to tell everyone your name and what organization you're from, just so that I should have done that, but
okay, my name is Carla Ostov. I am an HPC researcher and from the National Laboratory for Scientific Computing in Brazil. And I also a part of the group that is responsible for Santos Dumont supercomputer. So we run the supercomputer. We also promote schools, and we also help users to use the machine in an efficient way. And we also help to build ports. Also, we have a very interesting work, and it's nice to be part of the Americas collaboration and to be a member too. Thank you very much.
Thank you, Carla. Let's see, Paula, since you're as one of the other coordinator, I just wanted to mention Paula Bergelet is one of the, between Carla, Paula, and myself, we're sort of trying to launch a chapter, but we're hoping to get more people involved so we can grow the organization committee and establish activities and have more regular opportunities virtually, because we are a regional chapter, so people are spread out in many countries. But thank you for joining us today. And I hope to see, I also wanted to put a plug for the workshop that happened yesterday. The talks are recorded and available on YouTube. So if you want to go and watch the talks from the Women in HPC chapter in this CARLA, workshop at this CARLA, you can do that in the YouTube channel for CARLA conference. And with that, I wanted to pass the baton. We are going to kind of transition to our panel, open discussion / panel. But I wanted to pass the baton to Philippe, who was going to kind of lead that discussion.
Thank you, Veronica. Thank you. So I will share let's start the discussion in our panel. As moderator of this panel, I would like to invite people to open their camera, and let's start a discussion of cooperation in America. When we discuss about cooperation in America, we are discussing cooperation between countries, not just Latin America with USA, but between countries. So it can be between Argentina and Colombia, and so on. So the idea of this group, America Collaboration, is to improve the cooperation between groups, between labs, and to have a better research development in HPC. So I think that we can start with Silvio. Why Silvio? Because the two presentations of the papers, the first from Dario and the second from Luis, both were with Silvio from Argon. So can Silvio say something to us about how start this cooperation, how Argon open for access the machine, how the contact, the beginning of the research. I think it is very important to all the people to have an idea of start some kind of research together with other people.
Thanks, Philip. So yeah, I'm Silvio Ricci. I'm a computer scientist at the Argon Leadership Computing Facility. And so we run one of the leadership centers from the Department of Energy. Our sister facility is Oak Ridge Leadership Computing Facility, and we have Veronica and Benjamin representing that here. And so first I would like to say we've mentioned Argon a lot today, but there are other centers that are also open to the collaboration, right? Like as I said, the OLCF, the Oak Ridge Leadership Computing Facility, and there's also NERSC at Berkeley, plus the NSF sites like NCSA or the Texas Advanced Computing Center, or TAC. So there are multiple places that will be open to provide assistance, some computing time, and maybe training. And those are the main aspects that I would like to mention, right? And how I've been trying to help others through helping them obtain time on the supercomputers, and that is relatively easy because we have something called director's discretionary allocations. That is a small percentage of the total time available on the supercomputers per year, but still a lot of time. So that's probably at the Argon site, it's about 10% of the total core hours or node hours available, but that is still a lot. So that allows researchers to get on the machines, learn the programming environments there, and start experimenting, building their codes, and experimenting with scalability and performance optimizations. So that is one of the important aspects, and the second is the training and education aspect, right? And for that, I would like to mention the workshops that we run that are open to pretty much the entire international community. You just need to apply. And then there's another very important training program that is called ADPESC, and that is an abbreviation. And let's see if I remember the entire name. It's the Argon Training Program for Extreme Scale Computing, ADPESC. And I can provide links for that. So that happens once a year. And around August, and that is a very intensive training. It takes 2 weeks, of very intensive, courses and hands-on experience. It starts at 8 a.m. and ends at like 9 p.m. when it happens in person. When it's over Zoom, it's been a little bit more condensed to avoid people to keep people interested. So I recommend that, and I'm open to any questions, and happy to take any questions, and happy to help in whichever way I can. And as we said in the beginning, we're keeping it this discussion, or we started in English, but we're happy to transition to Spanish or Portuguese if needed, because we want people to talk to us, right? So we don't want language to be a barrier here. So that's pretty much all I have to say, Philip.
Yeah, if I'm a student, I can take this course. Can I access the machine, or did I need to be in a group, on a research group, to have access to the machines or to the course?
And in terms of accessing the machine, remember that Dario mentioned he got an allocation himself, right? So you can be an individual applying for that. So there's no need to be part of a group. Individuals can apply, and the process is simple. You just need to describe your goals, your research goals, the science of your project, what are the resources that you expect to use, what are the needs in terms of, core hours or node hours, and things like that, right? And we can all help answering those questions and preparing a good application, a competitive application.
Yeah, very nice, very nice.
And in terms of the training, right? You can also apply as an individual. In fact, the ADPEX, for example, that training program is directed to graduate students, postdocs, and early career persons. So it is targeted to individuals. So it's about preparing the next generation of computer scientists in HPC. And some of the material, I think it's available on YouTube. So if you search, or if you go to the site, there should be links to recordings of previous presentations for those interested.
Yeah, and can you say something, Benjamin or Veronica, in Oak Ridge is the same thing as in Argon, or is it different, the access and how to apply?
Yeah, hello, my name is Benjamin Hernandez from Oak Ridge Leadership Computing Facility. I am a computer scientist. So regarding your question, yes, well, the point here is that ALCF, Argon Leadership Computing Facility, Oak Ridge Leadership Computing Facility, and NERSC are facilities sponsored by the Department of Energy. So in general terms, at least, the leadership computing facilities have a pretty similar programs. So we have three main programs, which are the big ones, which are Insight and ALCC programs, and the other one that Silvio was talking about is the Director Discretionary. So I could tell that the process is quite similar, but the review process is different, right? Every facility manage their program according to the user needs and also according to the HPC infrastructure that each facility is providing. So for that reason, in that sense, is quite different. But yeah, the main point here, I believe that, for example, at some point, the two facilities will use GPU technology, and GPU technology which won't be NVIDIA, right? So one of the important points here is to have or to inspect the readiness of the project, right? That means how well the code, the simulation code, and so on, can take advantage of the infrastructure that the leadership computing facilities are providing. So yeah, that's another important point. And for that reason, I want to emphasize that our collaboration is not just focusing on infrastructure, but also in training and outreach. As Silvio mentioned, the ADPESC program, the DOE together with, the leadership computing facilities together with other companies provides hackathons. And in this particular case, those hackathons helps the users to get ready their code to these machines, right? So also training it's very important to us to make proper use of the infrastructure, and also I would like for you to think not about maybe a compute capability, right? In terms of modeling and simulation. Right now, both facilities are open in projects such as machine learning, as Eliu showed in his keynote, machine learning, data analytics, visualization project, as Luis also showed and Dario showed in their talks, right? So we are broadening the scope of the applications that are being accepted. And for example, let's say for machine learning and deep learning, we are getting ready the software stack, which usually depends of libraries such as TensorFlow or PyTorch. So you can get the most of the machine by using this customized version of this software stack. The same applies for data analytics. I could say the same applies for visualization. On the other hand, if you have a modeling, a traditional modeling and simulation problem, what I've seen in this collaboration with the Latin American colleges is that there are like two flavors, right? Or maybe three. The first one is those teams who are developing their own code, right? For example, the group from Costa Rica, led by Esteban Meneses, they are building their own simulation codes, right? And on the other hand, we have, well, I've noticed that there are another kind of research group where maybe they already are using a simulation code that already, it already scales at Argon or octubre, for example, GROMACS, for example, NAND, and so on. So if you find, as a researcher, you find that you may need more resolution in your simulation, or you need to temporal resolution, spatial resolution, larger scale data analysis overall. This by using these simulation codes that already runs in these facilities. Also, it's a good opportunity for you to collaborate with us. Yeah.
Yeah. I'm seeing in the chat that Robinson from Venezuela is sending a lot of different. Robinson, would you say something about your cooperation? I see here that you say that you had something with USA, Brazil, and Colombia. Can you explain for us? Hola, Robinson.
Hola. Thank you very much, Philip. No, it's just a comment. So we at Venezuela, as you all maybe now, we have a lot of problems right now. And for the last 2 or 3 years, our undergraduate or graduate courses in every area in HPC was done in collaboration. It's a real collaboration because this collaboration is born in the past CARLA events. And so we have a lot of friends, and those friends share with us their computational infrastructure, courses, workshops, and so on. So I think it's a very nice, beautiful way to collaborate. Also, not just only for research or for high infrastructure sharing, but also for teaching. And it is very important for us right now. And I am very, very pleased.
So you had this cooperation because you had friends in other countries, in other labs, and so they opened access to the machine, something like that.
Yes, that's a kind of unusual cooperation scheme, but it's useful also. That's only my comment. Thank you very much, Philippe.
Thank you, Robinson, for your explain. Okay, let's continue. Can we hear something about Carlos? Would you like to say something about the cooperation between countries?
Yes, in fact, one of the things that we told before is the main issues and problems that we have here from the side of the Latin American researchers or same for the students to make some attention for the calls of the different centers or different programs. So I want to hear more about this, the vision, for example, for Veronica, Silvio, and Benjamin, about this problem. No? For example, there are a few months ago, there are the I expect a call for proposals. We observed different issues. Of course, we talk about the problems that we detect in this application. So please, I think that it's a good moment to share this.
Yeah. Somebody want to say something about that?
I can probably say something. Carlos, you're mentioning the applications, right? That we notice that students do not write good applications, and in terms of writing in a concise way, in good English, and in a way that is convincing to someone reviewing it, right? So there's a lot of work that we should do in those aspects, and we'll be happy to try to help them.
Yeah. I see Esteban. Did you want to say something about Esteban Menezes de Costa Rica? Did you want to say something about your experience of cooperation? You had your PhD in Urbana-Champaign, and you returned to Costa Rica. So did you maintain cooperation with people from Urbana-Champaign, with Blue Water?
Yeah, thank you, Philippe. What you guys have been saying about the collaboration is quite important for people returning to their home countries after research experience. Yeah, after a research experience in maybe the US or Europe. I think it's quite important to keep those connections alive and strong. My own experience with Oak Ridge and Argon, and much of this has been through people here in this meeting. And it's been a great experience. We've been using Theta supercomputer for a year and a half. Silvio has been instrumental in that cooperation, and what I have found is that there are very few obstacles in using those large machines in the US. As long as you have the need and you justify it, I think is straightforward to go through the process of requesting an allocation. Same thing with Summit. We have a long-standing collaboration with Terry Jones at Oak Ridge. And through Terry, we have been able to run codes on Summit supercomputer and Titan supercomputer that was before. But in general, I feel that as long as you have the computational needs, those supercomputing centers will be interested in you becoming a user. So my experience has been very positive.
Yeah, Stephen, we are discussing the use of infrastructure, not the use of computing possibilities. But what I'm thinking about is this beginning of work access machines give you the opportunity to work together with researchers from US, or is just the access to the machine?
I think we have both cases. in one
because
case,
in my opinion, what is important is exactly the cooperation between the researchers, between the different groups, is how we can grow with the research, grow with the Latin America experience, and had a better research of quality. No?
Yeah, I agree, Philippe. I think that's the most valuable asset in a corporation, having colleagues at those centers. Yeah, we have that experience also to incorporating new people to the team from abroad. But I think it's more kind of an organic process, right? You start maybe using the machine, and then you start making some connections, and suddenly you have a cooperation or a collaboration with those colleagues. Yeah.
Yeah, very nice. Let's change a little. We are just talking about USA. Why not here? I see Tadeu. Tadeu, did you want to say something to us about or CARLA to access the machines in Brazil? CARLA Ostolfo or Antonio Tadeu, how we can use the Santos Dumont machines?
Por favor, de servicio, voz para Antonio Tadeu.
Tadeu opened his camera, but not his mood. Oh, CARLA is there, and Antonio. They don't have access.
I just enabled.
Okay.
Sorry,
no, it's okay.
Thank you, Veronica.
You can't speak. You can't speak.
I was feeling censored. I was worried. Thank you. Don't worry.
Go ahead, Tadeu.
It's funny because I was actually discussing with CARLA Ostolfo, I mean, about that at this exactly moment. I was discussing with her about the presentations that we had today, in particular the one from Dario that sparked the discussion or the feeling of having to discuss this with CARLA, because here in Brazil we have a different funding scheme, which makes things quite different from what happens in the US. Yes. So, for instance, if I'm not mistaken, it was let me see. It was Veronica who said in the chat about the different programs, the big programs in SITE and RACC, and the discretionary program. If I'm not mistaken, Veronica, you can confirm this to us. These big programs, they have funding from NSF or something like that. And these funding agencies, they kind of pass resources, funding resources to the center for it to be able to hire people to support these big projects. Am I right in my?
Sort of, except for the NSF part. We're mostly funded by DOE Office of Science, and they basically send the funding from government, like Department of Energy in the US sends funding to us for the computing facility, and that includes both the funding to put the facility together, like deploy the supercomputer, and support, staff support for however long the machine is available. So computational scientists are funded, and our support team is funded to basically help the users. So that's their main primary job. And computational scientists get assigned to a project, and then sometimes it varies. It could be 50% of the time to a project, and 50% of the time they do their own research, but they are funded by the facility that is funded by government.
Okay. Yeah, because here, I mean, we have funding from the government to support the operation of our supercomputer, the Santos Dumont computer. but it's I mean it's for a very basic operation. So basically energy and the people that give the end user support. And but for instance, to help the users to better parallelize or to optimize their code, we have a group that CARLA heads at NCC, but it's a small group that has some difficulty in increasing its human capacity to provide this service to many projects. So we have a kind of a bottleneck to provide this sort of service. So in the end, what happens is that it's difficult for us to separate big projects from small projects. So basically have the same small team that must give both operational and parallelization and optimization support for these different projects. And this I think is something that doesn't help us in the best way to manage our resources. But I mean, the way that we deal with proposals is quite similar, I guess, with the centers in US. In fact, we read a lot about what you do in terms of evaluation, also some centers in Europe, such as BSC and others. And it's pretty much the same process. So we have an advising committee that reviews the projects. We also sometimes also resort to some ad hoc reviews, and they evaluate the quality in terms of the research that's being proposed, and also on the need and promptness to use supercomputing facilities. But it's difficult for us because of the size of the group and the demands that the number of demands that we receive from proposals. For instance, to help these proponents to improve the quality of their proposals in terms of the specification of the resources that they want, or on the usage of some versions of code that could be used instead of others that they propose, because sometimes the scientist is used to a specific version of a solver or a simulator. So just a second. Sorry, my cat is complaining. I'd like to sort out.
No worries.
So I think this is the main bottleneck: human resources to help both people which propose projects and people for helping the projects that have been approved to use the best efficient way the machine. I don't know if CARLA would like to complement what I said.
Let's see if CARLA wants to say something. CARLA, stop.
Okay, she said it's okay. I think that's one, and it's a very good point. And even in at ORNL, like the big projects are already usually like they've proven that they can run a scale. It's not like they need like help like from zero to let me parallelize my code. Like they have to in order to get like millions of allocation hours, like you have to have proven that you could run. So I think we do have a gap for the director discretionary projects because they don't get a computational liaison. So they're sort of like, here you go, here's the time, and they don't get a scientist to help them. So whenever you submit a ticket, their user assistance team will try to help with like specific issues, but they're not gonna have the cycles to help you port your code. So I think that's an area that I think we could do better at, and maybe find a way to grow those projects so that they're, because eventually the director discretionary is a stepping stone so that you are able to apply to a bigger allocation in the future. But without that extra help, a lot of the discretionary projects may not be able to get to the next step. They'll just live for that 1 year or two and then go away because we don't have a dedicated staff to assign to each director discretionary project either. So I think, yeah, there is a gap for sure.
Very well. There is Maria Ruiz with some questions, but I think that Silvio answered, no? Did you want to ask something or say something, Maria?
I think everybody's muted, it looks like. So if you want to have a question, maybe you have to raise your hand so we can unmute you.
Yes. Has to unmute. Did you want to unmute? Yes. You say something? No. Okay. So we are going to the end of panel. We need to end this session. I will ask if there is somebody that want to say something about the cooperation. I see Carlos. Carlos, did you want to say something?
Yes, of course, to invite all this panel for the next both in supercomputing conference about this collaboration. So in this panel, of course, we start to take some question about the possibilities of interaction in the continent. And now the idea is also to discuss with the people of Canada, of course, of the USA. So see you in AC 21. If you want also more information about us, about the collaboration, the different centers and people that participate. So we write in the chat of this Zoom room, the address of the site, and also for the people that want to join in the Slack channel. Also, we put in the chat the coordinates to join us in the Slack.
Yes, we will see. There are two people with Antonio and Maria. Please, Antonio, go ahead.
Thank you, Navo. Although I'm not Antonio, I'm Tadeu, but it's okay.
But you are Antonio Tadeu Gomes. Please.
If you come like that in the streets.
Okay, if you understand, Gomes. Go ahead, Gomes.
No, I was just to complement my intervention. I forgot to mention something important. Besides these operations that operation staff and also parallelization, optimization staff that helps as best as possible the users of the Santos Dumont facility. We also have the Santos Dumont summer schools, which are an important aspect also of our service, because with that we can train the users and use the Santos Dumont machine as a machine for those training courses. Carla Stoff is the one that heads this summer school every year at the UNCC. The last summer school, which was in the beginning of this year, was completely online. And if I'm not mistaken, we had a lot of participation from people from the rest of Latin America. It was something nice. As Dario mentioned, even though it's something that you shouldn't say it is good, but it let's say, showed us that these virtual meetings have their advantage. And one of those advantages was really that we were able to provide these summer schools to people outside Brazil.
Thank you. Thank you, Tadeu. There is Maria with, please, go ahead, Maria.
Hello, everyone. Just wanted to comment about the reason for my question. I thought it was very interesting what was mentioned about having all these programs by the leadership class facilities in the US to train people. Unfortunately, what I have seen so far is that those resources are open only to people who are already in the HPC field who are already working toward optimizing an application. So even though somebody said, yes, individuals are welcome, well, those individuals have to have something going on already. At least that's what I have seen. So I just wanted to get a realistic view of who can access those resources. It's not just anybody, and not just for not for any purpose, right? For what I've seen, people have to have something already in the works. It'll be great if more resources were open to people who would want to learn to get into the HPC field, because it's not easy to get time on those kinds of resources. Yes, Silvio mentioned there's a lot of training that are talks that are recorded and things like that. That sounds extremely valuable. Unfortunately, that cannot replace the experience of actually going and logging into a system, learning how to run an application, learning how to use a resource manager, learning of all the problems that you might encounter, while doing that. And that was the point of my question. So if anybody knows of anything like that, I mean, in my case, I've used I have experience in the HPC field, but not in all areas. And I thought it would be great for me to maybe delve in some areas that I don't have much experience in. But then we hit this wall. It's not easy. But then you have the cloud, and in the cloud you have providers like ARM and like AWS and other cloud services that do offer that sort of thing. So if we could emulate what they do a bit more to get more people into the field, I think that would be a great thing. Somebody mentioned the workshop at SC21. So just a reminder that the early registration is fast approaching. I believe the deadline is October 15. So if you want to register for that, then try to do it sooner rather than later so you don't miss the early registration. I believe since this is a workshop, and maybe Veronica would have more accurate information, since this is a workshop, that's on top of your technical registration. So you get a discount if you register early, you get a discount if you are an ACM or IEEE member. So that can bring your technical registration a bit down. But then if you want to attend the workshop, that's in addition to the technical registration. And again, maybe Veronica knows better, but it can add up. Or there is the option to just attend the workshop and register for that. But that's, it can get expensive as well. So just go and look at the registration page and check that out. But the deadline for early registration is October 15.
Yes, thank you,
Maria. Just one small comment. It's above this year at SC. Like, we're doing a workshop at CARLA, but at SC will be above. So there shouldn't be any extra charge other than if you're already attending SC, it should be okay.
That's amazing, because many of us cannot afford that. That's great news. Thank you, Veronica, for the clarification. Okay. That's awesome.
Thank you. Let's finish. There is Esteban and Carla that want to say something. Please, Esteban, did you want to go ahead?
Yeah, no, just a quick comment on Maria's question. I think that's a really important point. On the sophistication of, potential attendees to these trainings. I understand that some trainings in the US require a higher entry point, people coming with their own codes and looking for scaling those codes to a large number of cores, say. And there are other people who really want to learn something about HPC and have a lower entry point. Maria, I think in the Latin American continent, there are a few options for that people. In Costa Rica, we have an HPC school that has a lower entry point meant for people who really don't have any previous, experience in HPC, but at least they know a little bit of computer programming. So we take those students and teach them, MPI, OpenMP. I understand the Santos Dumont training has a similar entry point, but I guess Carla will refer to that. But I can see other options for people without a lot of experience in HPC in Latin America, and I think throughout SCALAC we can provide those trainings for those people. So I'm going to ask Carlos if you can put the SCALAC website link on the chat, so that people can look at the resources that we have available.
Perfecto. Thank you, Esteban. Yeah, it's okay. Let's, Carla. Okay, let's go. You need to be on mute.
Oh, okay. So I just would like to give one more information about that. I think that
the end of the panel. Go ahead.
If we really want to open for more users, I think we have to invest also, not only in HPC training, but we also need to invest in portals. So what we have done here in Brazil, we have developed a portal for the people from the Botanic Garden. They didn't know anything about computer, and they are not able, they don't feel able to work on it. So we develop a very user-friendly portal for them to submit models, to analyze models, and to input data, to see data, to analyze data. So, and we are doing something very similar with the people that Karen, that from the BO portal, are coordinating for the people from bioinformatics. So those are people that I think they don't want to learn HPCs. So we have to think that there is two kinds of people. There's the people that are willing to understand and want, like physicists and chemistry, and they want to develop their own program. Those people, we make the training. But we also have the people that are users, and they want to have a system for them to submit the problem. I think we have to think about developing very user-friendly portals for such a kind of users. It's different. That's all.
Okay, thank you very much for your mentions. So we need to close our, thank you all for your answer to all the questions. And as Carlos said, we will be in supercomputing in November with above, and next year we will be another time in CARLA discussing cooperation and collaboration in America. This is very important, and we want to improve this all the time, and this is the idea of this group. I ask somebody if you want to say the last words. Veronica, as you start, did you want to say the last, or Esteban?
I think Benjamin was on the hook for that.
Yeah, well, just to conclude this workshop, thank you everybody, in particular to the CARLA Organization Committee, our speakers, Elio, Dario, and Luis. And well, just to summarize, what we look in this collaboration is a collaboration in terms of science, but also in infrastructure, right? In particular, support for access to HPC resources. What we want to provide here is advice during the life cycle of your project. In these terms is from project application to deployment of your simulation, your deep learning, your data analysis or visualization workload. And also we are quite interested in training. And yeah, it is important to mention that our users need to have HPC background, right? And for this reason, it is important the collaboration with Latin America, as Esteban mentioned, with their training networks and so on, right? And finally, outreach. In order to, one important thing that we have at DOE is that we promote the science that is being done for our users. For that reason, if we can have outreach, highlights of what we are doing with this collaboration will be great, because it will improve the support at long term. That's it. Thank you all.
Thank you. So thank you all people, all the organization and the people from CARLA, Isidoro, Liz, and other people. Thank you for all. And we are closing our panel and also, I think so, our workshop. Okay. Bye-bye.
Thank you all.
CARLA, Veronica, go ahead, Veronica.
I know, thank you for everybody, for everything. I think it went great, and I hope to see more submissions from everybody that commented today or next year. And see you at the BOF in November.
Bye-bye.
Boundary.